video is for Unit 7 Biomechanics in Sport and Exercise Science, looking at 7.3 assignment about angular motion, and just the second video really in a couple on levers for C3. Now this video just builds on the previous one. We've already looked at what mechanical efficiency refers to, and it's this relationship and organisation of the components of a lever system to figure out whether any given lever system has mechanical advantage or mechanical disadvantage. And hopefully you remember that that means if the effort arm is bigger than the load arm, then that lever system is great for strength and force generation, but not so great for range of movement and speed of movement. And that typically would be our second class lever systems, where the load arm is between and in the middle between the other two components, the effort and the fulcrum. Conversely, if the load arm is greater than the effort arm, then a given lever system is great for speed and range of movement, but not so good for strength and force generation. And broadly speaking, that's our third class lever systems. But we've just got to understand how to calculate mechanical advantage. And the way we do that is by using a very simple equation where we look at the effort arm length and divide it by the load arm length. And whatever number we get from that, we can determine whether there is numerically mechanical advantage or disadvantage. So there is mechanical advantage if the number at the end of this calculation, this equation, is greater than 1. So if the number is greater than 1, there is mechanical advantage. And what the implications of that are, we actually need less effort to move the load to, deal with the resistance, and that makes it mechanically advantageous for strength. It's not great for range of movement. We've got to move a lot further to get range of movement. But if the value is above 1, then it means that proportionally we don't need as much effort or force generated by our muscles to respond to the resistance. Conversely, if the number at the end of this calculation is smaller than 1, then what that means is we have a system which is great for range of speed of movement, but the effort required, the force that's going to need to be generated, is proportionally quite large compared to the load. We need to generate a big force to move that load. So above 1, mechanical advantage; below 1, we would deem there to be mechanical disadvantage. Let's have a look at some examples to hopefully put this into practice. So on this top example to start off with, green is the effort arm. The distance is 0.5 and the effort arm is 0.5 meters and the load arm is 0.1 meters. So we have to do the maths. We have to put the 0.5 over the 0.1, which gives us a mechanical advantage of 5. Because 5 is greater than 1, we would deem this lever system to have mechanical advantage. Now, if we had a lever system whereby the effort arm was 0.1 and the load arm was 0.5, we do the same sums. We do 0.1 over 0.5, and we would see that the mechanical advantage outcome is 0.2, and that means there is mechanical disadvantage because the load arm is greater than the effort arm. So having looked at how to calculate mechanical advantage, it's about the effort arm over the load arm. If it's greater than 1, there is mechanical advantage. Just to recap, second class levers, for example, our ankle joint, are designed and would have a mechanical advantage greater than 1. The effort is always longer than the load because the load is in the middle. So second class levers always have a mechanical advantage greater than 1, and you can give some actual numbers to that if you like. First class levers, hopefully we already know that depends on where the fulcrum is, which other components it's nearer to determine whether there's mechanical advantage or not. If the fulcrum's closer to the load, then there would be mechanical advantage because the effort arm is going to be bigger. Now, looking at mechanical disadvantage, we know that in third-class lever systems, the load is always greater. The load is always further away from the fulcrum because the effort's in the middle. FLE, third-class lever, the effort's in the middle, which means the load arm's always greater. We know that if the load arm's greater, the mechanical advantage number is going to be less than 1. Third-class lever systems are not great for force generation. To move our limbs with these third-class levers, we have to apply a relatively big effort. We can't change where the effort is exerted. We can't change the length of the effort arm because it's our body, it's how we're built. What that means is this hip flexor muscle here has to generate quite a big effort, force, to move the load of our leg. And again, first-class lever systems, it depends where the fulcrum is to determine whether there's mechanical advantage or disadvantage. If the fulcrum was closer to the effort, what that means is the load arm is bigger, then there would be mechanical disadvantage. Now, these are kind of examples, but they're also a little bit, I guess, icing content, a little bit more advanced content. I've just tried to give you some examples of numbers and the equation, effort arm length over load arm length. So these are first-class levers. The fulcrum is in the middle in all of these examples. The first example is the effort arm and the load arm. Ignore those different bits of language. They mean the same. Force means effort, resistance means load. So the effort arm and the load arm are both 10, which means 10 over 10 is 1. This would be equilibrium. There's no advantage or disadvantage. They negate each other. In this example, the fulcrum is much nearer the load, so the load arm is shorter, the effort arm is bigger, which gives us a mechanical 15 and 3. So the equation would be 15 divided by 5, not 3, sorry. 15 divided by 5 gives us a mechanical advantage of 3. Now, given that the value is greater than 1, that means it is a mechanically efficient lever system. So this is great for force. The effort can be relatively small to move the load. The reverse of that is if the fulcrum is nearer the effort arm, which gives us a small, short effort arm and a longer load arm. So now we're doing the equation of 5 divided by 15, which gives us a mechanical advantage of 0.33. This is mechanical disadvantage. The effort, this little effort arm has to generate the force needed to move this long load arm is proportionally huge. So again, remember that internal lever systems in our body we can't change, but if there are bits of equipment where we can modify where the load is or where the effort arm is, then, how close or far apart they are, then we might be able to change the mechanical efficiency to some degree. So in this example, the effort arm is 20, the load arm is 10, so 20 over 10 gives us a mechanical advantage of 2. So it's great for force production. Relatively small force is needed to move that load. If, however, for any reason, we moved the load nearer the fulcrum, we get 20 is our effort arm still, but now the load arm is only 5. So we get 20 divided by 5, which gives us a mechanical advantage of 4. So if we were able to manipulate that, that makes this activity even easier. We haven't changed the load. It's still the same amount of load, but we've moved where it is in relation to the fulcrum. And by moving the load nearer the fulcrum, this is an easier load to move. This is an easier activity. Conversely, if we shifted the load nearer the effort, then we've got a effort arm of 20 and a load arm of 15, which only gives us a mechanical advantage of 1.33. Is it still mechanically advantageous? Yes, but relatively small advantage compared to both of the other two options. So shifting where the load is, if it's possible in a sport, can vary how much advantage we get in second-class levers. If it's within the body, we can't change it at all. What about this as an example? So most lever systems in our body of third-class lever systems. So what we've got, if we look at the shoulder joint, we've got the fulcrum, we've got the deltoid, the middle deltoid that attaches on the humerus at the deltoid tuberosity. So the fulcrum's on the right, the effort would be next, and the load is the forearm and this dumbbell over here. So it goes load, effort, fulcrum. It's a third-class lever system with E in the middle, FLE. Now, the athlete doing a straight arm, lateral, sideways dumbbell raise, we have this fulcrum, this long load arm, and this relatively short effort arm. Now, that's pretty tough. That's quite a hard activity. And all I wanted to show you really here is that we can manipulate by the position of our arm how long this load arm is. So this athlete on the right here has done a bent arm lateral dumbbell raise. So what they've done then is they have, that's moved, sorry. The fulcrum is still the shoulder joint, but the load arm you hopefully can see with a bent arm is relatively short compared to the load arm. So they've reduced the difficulty or that the load arm presents. They've reduced the distance, the length of the load arm. The efforts obviously, so the fulcrum and effort haven't changed. They're the same. It's the shoulder joint and the deltoid attachment. But by manipulating the technique, we've decreased the load arm length and therefore changed how mechanically disadvantaged we are. We've made it a bit less. So sometimes the technique can help us make it harder or make it easier, and we can change the challenge for ourselves by doing that. So let's just look at these again, images and diagrams to illustrate third-class lever system manipulation, if it is possible to change any factors relating to this. So if you've got a load arm of 20, a force arm of 10, sorry, I should say a load arm and an effort arm, what we've got is 10 over 20. So the effort arm is 10, the load arm is 20. That gives us a mechanical advantage of 0.5. So we can see that there's mechanical disadvantage always in these third-class lever systems. Always the load arm is going to be greater than the effort arm. However, if we can manipulate the extent to which they are different, we can either make it harder or easier. So in my dumbbell example, my lateral dumbbell raise, we had a very long load arm and a relatively short force arm. So this sum would be 5 for the effort arm over 20 for the load arm, which gives us a challenge, a mechanical advantage of only 0.25. This is a disadvantage to us for force generation. Great for range of movement, but terrible for force generation. So my little deltoid muscle would have to work incredibly hard to move the load of my arm and the dumbbell. If we can change that somehow, I mean, in this example, the effort has moved. I would suggest that the example I showed you before with the dumbbell was the load moving. But if we change the ratio between the load arm and the effort arm, in this case now it'd be 15 over 20, we give a slightly greater mechanical advantage or slightly less mechanical disadvantage. So either by moving the load or by moving the effort in relation to each other, we can adjust how much mechanical advantage or disadvantage there is. So that was pretty tough content, I'd say, and as I said earlier, I'd say that was icing content. If you can get your head around manipulating those variables, if it is possible, and think of some examples, then that's great. How about this for some application though? Looking at tennis players. Tennis players tend to be fairly tall. Obviously, males tend to be taller than females, but if you looked at tennis players, generally speaking, overall, I'd certainly say that they were relatively tall athletes. Now, what's this got to do with lever systems? Well, we know already that reach, I guess, even if you're playing at the net, the reach that you can cover is an advantage. But something like serving, where you've got this great range of movement, remember, these are third-class lever systems. They're not so great for force generation. They're much better for range of movement and speed of motion. So a tennis player doing a serve can firstly make contact with the ball really high up, which gets them the opportunity to hit more downward over the net and get an advantage, as opposed to if you're shorter, you've kind of got to hit along or up and over the net if you're really short. So they gain this greater range of movement anyway. But they are also quite strong athletes, and they will be able to generate great angular momentum, angular velocity, because they're strong as well. So they can, move the racket through the range of movement quickly and powerfully to generate greater angular velocity, so that when they make contact with the ball, obviously they generate big power on the ball. Just looking at the height of rankings, so the top 10 rankings, tennis players are all relatively tall compared to those that are in the lower rankings. There is a correlation, a relationship between tennis player height and success. And this top graph actually looks at typical females and male height in the world of tennis players. So, a long time ago, 100 years ago plus, both males and females were relatively short. As time has passed, tennis players have, we have all probably become taller, but successful tennis players are taller, and that, I guess, reinforces that point. So throughout these sections of your work, remember, you must give a range of sporting examples to show your understanding of these biomechanical concepts of lever systems, but you must also give some gymnastics examples as well. Just to finish, here's the specification of the first two topics we've covered in lever systems. So we've looked at the structure, the types of levers, and how they function. Do they offer strength and resistance with little effort, or do they offer a high speed or range of movement? The final video in this section will be on turning effects.